System Integration Addendum 2, Quantum Lagrange Array Gravitational Interferometer and Buckyball Stabilized Superfluid Vortex Gyroscope. Section B MANSA Skin Integration. Multifunctional Adaptive Nanocarbon Surface Architecture as Integrated Infrastructure for the QLAG BBG-SVG Navigation System. Authors: Chris D. Seeley and Brad Yocum. Date: May 2026. Status: Provisional, cross-referenced to QLAG, BBG-SVG, and MANSA standalone provisional. Docket No. B.0 Purpose and Scope. The QLAG system disclosure establishes the Lagrange-point BEC-MASER frequency standard network and the parametric transducer architecture for quantum-coherent signal coupling. The BBG-SVG disclosure establishes the superfluid vortex gyroscope as the primary inertial navigation sensor, phase-locked to the QLAG network. Those two documents together describe the navigation metrology system. They do not address how the navigation system integrates with the vehicle surface, how the QLAG phase reference is physically distributed on the vehicle, how the cryogenic environment of the BBG-SVG squid is thermally stabilized, or how the vehicle's outer boundary is protected against the atomic oxygen and ultraviolet flux that would otherwise degrade the quantum sensor interfaces. This Section B addendum addresses those gaps. It describes the multifunctional adaptive nanocarbon surface architecture, disclosed in full in the co-pending MANSA standalone provisional by Seeley and Yocum. May 2026, specifically in its role as the integrated surface infrastructure for the QLAG BBG-SVG system. Section B is intended to be read as part of the combined QLAG BBG-SVG system disclosure, alongside Section A and the QLAG parent document. The MANSA standalone provisional covers the surface architecture in full generality. This addendum covers only those aspects relevant to QLAG BBG-SVG integration and the combined system performance they enable. B.1 Phase Reference Distribution, MANSA as QLAG backbone. B.1.1 The distribution problem. The BBG-SVG gyroscope requires its squid local oscillator and second sound heater drive to be phase-locked to the QLAG BEC-MASER carrier at 6.8 GHz. In the QLAG parent disclosure, this lock is achieved by the parametric transducer with interaction Hamiltonian H int equals G, which transfers the MASER phase to the squid output. The transducer operates at the gyro substrate. The physical question not addressed in the prior disclosures is: how does the 6.8 GHz reference get from the QLAG terminal to the BBG-SVG substrate, which may be located anywhere on the vehicle interior or exterior? In conventional spacecraft design, this would be solved by a coaxial RF harness, a length of semi-rigid or flexible coaxial cable running from the QLAG terminal to the gyro. This solution has three disadvantages. First, a coaxial cable of length L has electrical length that varies with temperature as dL, dt approximately equals L alpha, where alpha is the linear thermal expansion coefficient of the cable dielectric. For L equals 0.5 meters and a day-night temperature excursion of 150 K, the electrical length changes by approximately 3.8 to 11 millimeters, corresponding to a phase shift of approximately 90 to 260 mRad at 6.8 GHz. This exceeds the capture range of the BBG-SVG phase lock loop by 1 to 2 orders of magnitude without additional thermal compensation. Second, a coaxial harness to a cryogenic substrate requires a thermal break that introduces impedance discontinuities and phase uncertainty. Third, the harness adds mass, volume, and routing constraints to the vehicle design. B.1.2 MANSA CPW sublayer as distribution network. The MANSA QLAG interface sublayer, described in the MANSA standalone provisional section 4, resolves all three issues. A subset of the MANSA graphene patches in layer 2 is configured as a coplanar waveguide transmission line network on the alumina substrate, operating at 6.8 GHz with characteristic impedance of 50 ohms. The center conductor width is 200 to 500 micrometers, gap width is 100 to 250 micrometers. Conductor material is gold deposited by sputtering on the graphene surface. The QLAG terminal on the vehicle injects the 6.8 GHz BEC-MASER reference into the CPW network at a feed point. The network routes the signal across the vehicle skin surface to one or more tap points, where a coaxial to CPW transition connector delivers the reference to the BBG-SVG substrate. Because the CPW conductor and dielectric are co-located on the MANSA panel, the network is isothermal with the panel surface at each point. Its temperature is. Reading Guide. Section B.1 describes the phase reference distribution interface between MANSA and BBG-SVG. Section B.2 covers MANSA thermal management of the BBG-SVG cryostat. Section B.3 covers AO and radiation protection of the quantum sensor interfaces. Section B.4 describes the distributed sensing contribution to navigation. Section B.5 presents combined system performance. Section B.6 contains interface specifications. Section B.7 contains the addendum claims. Controlled by the MANSA thermal router rather than by the routing path of a harness through the vehicle structure. The thermal expansion coefficient of gold on alumina is approximately 14 ppm, K. For L equals 0.5 meters and delta T equals 150 K, electrical length change is approximately 1.0 millimeters, corresponding to a phase shift of approximately 23 mRad at 6.8 GHz. This is substantially better than a PTFE coaxial harness. The MANSA thermal router further reduces the temperature excursion at the CPW lines. A GNR thermal spreader underlying the CPW traces reduces the peak-to-peak surface temperature swing to approximately 30 to 50 K for a well-designed panel, reducing the residual phase shift to approximately 5 to 8 mRad within the capture range of the BBG-SVG phase lock loop. B.1.3 Key result, phase distribution. The MANSA CPW sublayer reduces 6.8 GHz phase reference distribution jitter from approximately 90 to 260 mRad to less than 5 to 8 mRad, a reduction factor of 20 to 50 times, without a dedicated thermal compensation network and without added mass or cryogenic feed-throughs. In the QLAG, BBG-SVG, B.1.3 multi-terminal distribution. The CPW network is inherently branchable. A Wilkinson power divider or branch line coupler patterned in the same gold layer splits the reference to multiple output ports without reflection. A vehicle carrying 3 BBG-SVG gyros receives phase references to all three from the same MANSA panel network, with matched electrical path lengths to within plus or minus 0.1 mm by lithographic control during panel fabrication. This matched length distribution eliminates the inter-gyro phase offset that would arise if each gyro were referenced from an independent harness of unequal length. Additional QLAG synchronized instruments on the vehicle, atomic magnetometers, quantum gravimeters, or optical clocks that may fly as part of an extended QLAG payload, receive the 6.8 GHz reference from the same network. The MANSA panel thus functions as the quantum frequency backbone of the entire vehicle, distributing the Lagrange-point BEC-MASER reference to all instruments simultaneously from a single injection point. B.2 Thermal management, MANSA as cryostat thermal interface. B.2.1 The cryogenic challenge. The BBG-SVG Squid and Josephson weak link operate at 1.5-1.8 K. The superfluid helium-4 reservoir must be maintained below the lambda transition at 2.1768 Ka. Cryocooler, pulse tube or Joule-Thomson, provides the cold stage, consuming approximately 20 W of electrical power and rejecting approximately 25 to 30 W of thermal power to its hot sink. The hot sink in a conventional cryocooler design is a radiator panel on the vehicle exterior. Key result, phase distribution. The MANSA CPW sublayer reduces 6.8 GHz phase reference distribution jitter from approximately 90 to 260 mRad to less than 5 to 8 mRad, a reduction factor of 20 to 50 times, without a dedicated thermal compensation network and without added mass or cryogenic feed-throughs. In the QLAG BBG-SVG system, the MANSA skin provides this radiator function while simultaneously providing its programmable thermal management capability. The relevant question is, can the MANSA panel, with its adaptive emissivity and high and plane thermal conductivity, serve as the cryocooler hot sink radiator more effectively than a conventional fixed emissivity radiator panel? B.2.2 Adaptive Radiator Performance. A conventional spacecraft radiator painted with optical white paint and LEO rejects heat at a rate Q rad equals epsilon sigma Ta, where T is the panel temperature and A is the area. At T equals 280 K and epsilon equals 0.90, Q rad approximately equals 280 W per square meter. However, the effective rejection rate depends on eclipse fraction, panel orientation, and the balance between solar absorption and thermal emission. A white painted panel facing the sun absorbs approximately 170 W per square meter, reducing net rejection to approximately 110 W per square meter in direct sunlight. The MANSA panel, when its emissivity is set to 0.57 and gate voltage is adjusted to minimize solar absorptivity in the visible band, rejects Q rad approximately equals 0.57 times sigma times T approximately equals 178 W per square meter at T equals 280 K in the IR, with negligible visible absorption. The net rejection in direct sunlight is therefore approximately 175 W per square meter. Comparable to or better than the white paint panel for the same area, while retaining the ability to reduce emissivity to 0.41 during eclipse to maintain panel temperature and reduce the thermal gradient seen by the underlying cryocooler cold stage. The critical advantage is dynamic response. When the cryocooler heat load increases, for example, during a high-rate gyro maneuver or following a thermal disturbance, the MANSA control system raises emissivity on the radiator patch subset within microseconds, increasing rejection capacity before the cryocooler cold stage temperature has time to rise. This is thermodynamic feed-forward control, not available with any fixed emissivity panel. B.2.3 In plane thermal spreading for hotspot management. The cryocooler hot sink interface is a point or small area thermal contact. Without lateral spreading, this produces a hot spot in the radiator panel that can drive the local panel temperature well above the mean. The MANSA Layer 3 GNR thermal router spreads the cryocooler heat rejection footprint across the full panel area in milliseconds, eliminating the hot spot and presenting a nearly isothermal radiating surface to the thermal environment. For a 0.1 square meters panel with in-plane conductivity of 2,000 W per meter K and thickness of 2 micrometers, the effective lateral conduction resistance is approximately 2.5 times 10 to the power of 4 kW, negligible relative to the radiation resistance of the same panel, which is approximately 0.018 kW at 280 K. The panel is therefore effectively isothermal, and the radiator operates at close to its theoretical maximum efficiency. The thermal router also buffers transient thermal pulses at the cryocooler interface. If the cryocooler undergoes a brief power cycle or operational transient, the GNR network absorbs the thermal pulse laterally before it reaches the gyro cold stage. For a pulse of 1 J over 100 milliseconds, the GNR layer stores and redistributes the energy across a 10 cm times 10 cm area in approximately 1 millisecond, limiting the cold stage temperature perturbation to well below 1 mK, orders of magnitude below the stability threshold of the second sound confinement resonator in the BBG-SVG. B.3 AO and radiation protection of quantum sensor interfaces. B.3.1 Josephson junction vulnerability. The BBG-SVG Josephson weak link is a 50 to 200 nanometers aperture in a silicon nitride membrane. The DC squid is a thin film superconducting loop on the same substrate. Both are fabricated with sub-micron feature sizes and are sensitive to surface contamination at the monolayer level. AL flux in LEO at 350 km altitude is approximately 10 to 10 O atoms per centimeter per second, and UV flux is approximately 8 to 12 W per meter. Direct AO exposure of the squid surface would oxidize the superconducting thin film, disrupting the Josephson junction characteristics within weeks to months depending on film thickness and operating temperature. The BBG-SVG gyro cell is enclosed in a cryogenic dewar, which provides some protection. However, the Josephson weak link interface must pass through the dewar wall to intersect the superfluid loop, and the associated mechanical feed-throughs and optical fiber access ports represent potential AO ingress pathways. The CPW tap connector between the MANSA panel and the BBG-SVG substrate is a similar AO exposure risk if not protected. B.3.2 MANSA as primary AO shield. The MANSA Layer 1 C60 functionalized passivation matrix provides the primary AO defense for all quantum sensor interfaces on the vehicle exterior. The mechanism is radical scavenging. AO impinging on the C60 layer generates C60 oxide intermediates rather than penetrating to the graphene layer below. The cross-linking chemistry provides a secondary response. Locally oxidized C60 molecules cross-link with neighbors, forming a denser matrix at the impact site that further reduces AO diffusion depth. Flux attenuation through the MANSA Layer 1 passivation is estimated from C60 polyurethane AO exposure data. At 100 nanometers layer thickness with 1.0 Wt% C60, the AO transmission is approximately 10⁻³ for fluences below 10 O per centimeter. This provides a 3 order of magnitude flux reduction at the layer 2 graphene surface and, by extension, at any quantum sensor interface covered by the MANSA panel. For the BBG-SVG CPW tap connector, a conformal MANSA patch applied over the connector housing provides equivalent protection without additional hermetic sealing. B.3.3 UV shielding and charge dissipation. UV irradiance of 8 to 12 W per meter in LEO includes wavelengths from 100 to 400 nanometers, of which the most energetically damaging for quantum sensors is deep UV, which can generate photoelectrons from superconducting surfaces and create color centers in optical fibers used for C60 spectroscopic verification. The MANSA Layer 1 C60 matrix absorbs strongly at wavelengths below 450 nanometers, with near total absorption for lambda less than 300 nanometers at 100 nanometers layer thickness. This provides effective VUV shielding for underlying layers. Charge accumulation on spacecraft surfaces in plasma environments can produce electrostatic discharge events that damage thin film sensors. The graphene layer 2 of MANSA provides a continuous conductive path that dissipates accumulated charge to a vehicle electrical ground reference. The control system sets the baseline graphene sheet resistance to provide charge dissipation with a time constant of approximately 1 to 10 milliseconds, fast enough to prevent ESD while slow enough not to introduce Johnson noise into the squid readout circuit. B.4 MANSA distributed sensing as navigation augmentation. B.4.1 thermal state map and gyro bias compensation. The BBG-SVG gyro bias stability of less than 1 × 10⁹ deg/hour is limited, as stated in the BBG-SVG disclosure, not by the sensor but by the second sound velocity's dependence on temperature. C2 varies with T near the lambda point. So a microkelvin level temperature variation in the superfluid reservoir changes the second sound resonance frequency and, through the second sound drive phase lock loop, may introduce a slow phase drift in the squid readout. The MANSA full surface thermal map, obtained by the gate voltage inversion method described in the MANSA standalone provisional section 7.3, provides a real-time spatial temperature map of the vehicle exterior at 1 to 10 mm resolution and approximately 100 mK accuracy. This map is used by the navigation computer to model the thermal gradient across the BBG-SVG cryostat mounting interface. Identify periods when the external thermal environment is introducing a systematic drift into the gyro temperature, and apply a model-based correction to the gyro output. The correction is a feed-forward term based on the measured external temperature gradient, applied before the gyro output is integrated into the navigation state. This extends the bias stability floor from its current temperature limited value toward the fundamental quantum limit. B.4.2 Plasma density sensing and ionospheric correction. The BBG-SVG gyro measures inertial angular rate in a reference frame fixed to the vehicle. In LEO, the vehicle reference frame is influenced by the Earth's gravitational gradient and by non-gravitational forces including atmospheric drag and solar radiation pressure. The navigation computer subtracts these to obtain the true inertial state. Atmospheric drag is proportional to the local neutral density, which is correlated with but not identical to the plasma density measured by the MANSA THC spectroscopy channel. The MANSA THC spectroscopic plasma density measurement, updated at each THC sensing cycle, provides an independent non-gravitational force estimator that supplements the gyro inertial measurement. When the navigation computer detects a transient neutral density event, the MANSA plasma measurement provides an early indicator that allows the navigation filter to adjust its drag model before the gyro output reflects the resulting trajectory perturbation. B.4.3 UV dosimetry is sensor health monitoring. The BBG-SVG C60 fullerene vortex marker is introduced by helium droplet pickup from vapor in the superfluid reservoir. Spectroscopic verification of marker presence, described in the BBG-SVG disclosure, relies on the HE-NC60 absorption shift of 0.072 nanometers per attached helium atom at the N equals 32 shell closure. This optical verification uses UV light from an internal fiber-coupled source. If the optical fiber access ports have suffered UV-induced solarization, the verification signal degrades. The MANSA UV dosimetry channel, measuring accumulated UV flux at the location of the fiber access ports on the vehicle exterior, provides a continuous estimate of fiber solarization dose, allowing the navigation computer to apply a time-varying correction to the optical verification signal amplitude. This extends the useful life of the spectroscopic verification capability and avoids false positive marker loss alerts that would otherwise trigger unnecessary sensor reconfiguration. B.5 Combined System Performance. The QLAG, BBG-SVG, MANSA integrated system provides capabilities not achievable by any combination of the three subsystems operating independently. The following table summarizes combined system performance and the integration pathways that enable each capability. The following table summarizes combined system performance and the integration pathways that enable each capability. Table B.1, Combined QLAG, BBG-SVG, MANSA system performance. Swap estimates are for a single-axis deep space navigation package. 3-axis IMU adds approximately 20 kg and 20 W. The most significant combined capability is the elimination of 3 traditionally separate spacecraft subsystems, the gyroscopic IMU, the thermal control system, and the RF distribution harness, in favor of a single integrated architecture. The mass saving is approximately 5 to 10 kilograms relative to a conventional deep space navigation package of equivalent performance, and the volume saving is significant given the compact MANSA panel geometry. For autonomous deep space operation, the critical advantage is fault tolerance. If the vehicle loses its Earth-based tracking link, the BBG-SVG provides inertial navigation. The MANSA THC communication link maintains connectivity to QLAG relay beacons, and the MANSA structural health monitor detects any hardware anomaly on the vehicle surface without ground visibility. The combined system provides navigation, communication, and health monitoring from a single integrated surface and sensor package, reducing mission risk from subsystem isolation in GPS-denied or communication blackout conditions. B.6 Interface Specifications. The following interface specifications define the electrical, thermal, and mechanical boundaries between the MANSA skin, the BBG-SVG gyro, and the QLAG terminal. The following interface specifications These specifications are normative for integration design and should be carried forward into the vehicle-level ICDs. Table B.2, MANSA, BBG-SVG, QLAG interface specifications. Low equals local oscillator. MPPT equals maximum power point tracking. GNC equals guidance, navigation, and control. SPW equals spacewire. B.7 Addendum claims. The following claims are supplemental to the claims in the QLAG parent disclosure and the BBG-SVG provisional. They cover the combined MANSA, BBG-SVG, QLAG integration specifically and are intended to be filed as part of the QLAG, BBG-SVG system integration document. They cross-reference the MANSA standalone provisional claims where appropriate. B1. An integrated spacecraft navigation and surface system comprising the superfluid Josephson gyroscope of the BBG-SVG provisional, the BEC-MASER frequency standard network of the QLAG provisional, and the multifunctional nanocarbon surface architecture of the MANSA provisional, wherein the surface architecture distributes the BEC-MASER phase reference to the gyroscope local oscillator via a coplanar waveguide transmission line network integrated within the surface architecture. B2. The system of claim B1, wherein the coplanar waveguide network operates at 6.8 GHz with characteristic impedance of 50 ohms. Distributes the BEC-MASER reference to a plurality of gyroscope substrates with path length matching to within plus or minus 0.1 mm. And maintains phase distribution jitter below 10 mRAD over a 150 K thermal excursion by means of the thermal routing layer of the surface architecture. B3. The system of claim B1, wherein the thermal routing layer of the surface architecture serves as the hot sink radiator for the gyroscope cryocooler, and wherein the programmable IR emissivity of the surface architecture provides dynamic feed-forward control of cryocooler heat rejection, maintaining the gyroscope superfluid reservoir below the lambda transition temperature during vehicle thermal transients. B4. The system of claim B1, wherein the UV active passivation layer of the surface architecture reduces atomic oxygen flux at all external quantum sensor interfaces by at least 3 orders of magnitude, and wherein accumulated UV dose at optical fiber access ports of the gyroscope is monitored by the UV dosimetry channel of the surface architecture and used by the navigation computer to apply a time-varying correction to gyroscope marker verification signal amplitude. B5. The system of claim B1, wherein the full surface thermal map provided by the surface architecture at 1 to 10 mm spatial resolution is used by the navigation filter to apply a model-based correction to the gyroscope bias output, extending the effective bias stability floor toward the quantum limited value by compensating for temperature-induced second sound velocity drift. B6. A method of integrated spacecraft navigation comprising operating the superfluid gyroscope of the BBG-SVG provisional as the primary inertial sensor, distributing the BEC-MASER phase reference to the gyroscope via the MANSA coplanar waveguide sublayer, managing cryocooler heat rejection via the MANSA adaptive emissivity radiator, protecting gyroscope external interfaces from atomic oxygen via the MANSA C60 passivation layer, and augmenting navigation filter accuracy using MANSA thermal map, plasma density, and UV dosimetry data as feed-forward correction inputs. B.8 Summary. The MANSA skin functions as the physical infrastructure that binds the QLAG and BBG-SVG instruments into a coherent spacecraft navigation system. It does this through 4 parallel integration pathways: phase reference distribution replacing the RF harness, adaptive thermal management supporting the cryostat, UV protection of the quantum sensor interfaces, and distributed sensing providing navigation filter corrections. Each pathway operates independently but they reinforce each other. The thermal router that stabilizes the CPW phase distribution also buffers the cryocooler transients, and the C60 passivation layer that protects the squid substrate also provides the UV dosimetry that monitors optical fiber health. The result is that the MANSA, BBG-SVG, QLAG system occupies the surface and sensor volume of 3 separately specified subsystems, a thermal control system, an RF distribution harness, and a precision navigation instrument, while delivering the performance of all 3 from an integrated architecture whose parts each serve multiple functions simultaneously. This is the practical engineering realization of the design principle stated in the MANSA standalone Provisional. The skin stops being passive, and the distinction between structure, thermal control, sensing, and communication disappears.